last time. What is?
That's the only one I remember.
Okay, we looked at agglomerative clustering.
Okay.
And we look at DBSCAN. Remember?
Yeah.
So we looked at DBSCAN, and by DBSCAN mean density-based. So that's where we have a density-based model where you have noise in the system, you have outlier, and you're able to have a good clustering. Okay. So let me share with you a summary. So we did look at the stage 9. So we looked at different algorithms, the K-means, the hierarchical, or also the agglomerative clustering. Then we look at DBSCAN. So we use DBSCAN when we have dense data, and we have applications with noise. So we use DBSCAN. Then we saw some strengths and weaknesses in each of the model. For instance, like you noted that K-means is good for centroid-based model, but when you have a spherical, non-spherical shape like the moon-like shape, so it struggles to fit in or to cluster appropriately. Hierarchical also, we looked at it as a model you use when you are exploring connectivity. For K-means, we don't really need K for it. So it's better than K-means. Then it does not do well in handling of noise, just like K-means. Then the DBSCAN, we don't need K for it. It can fit into any shape. It can cluster any shape, and it handles noise very well. So based on the data we explored in the last class, we established the fact that DBSCAN was indeed appropriate for such considerations. So we also did some work around round blobs, moons, concentric circles, elongated clusters, and we did find out some interesting pattern that K-means did great with round blobs. Hierarchical also did great with round blobs. DBSCAN did good. For moon-like shape, we saw that K-means failed, hierarchical failed, then DBSCAN did great. Then when we looked at the circles, again, K-means and hierarchical or agglomerative, they failed, while DBSCAN did fine. Then elongated shape or data set, K-means did okay, hierarchical did okay, but DBSCAN did good. So the key insights we drew from that were these: that K-means is good and is best actually for round, well-separated clusters, Hierarchical is similar to K-means, but gives you a dendrogram where you're able to you're able to visualize the connections between each cluster. So you're able to see how internally they are connected. So using dendrogram plotting. Then we noticed as well that DBSCAN filtered well for any shapes, weird shapes, even when you don't know K. So we came with a framework that we call the decision framework. And in this decision framework, we established that you go through this loop, you ask yourself this question: do you know how many clusters you want? Can you read it with me?
Yeah. Start. Do you know how many clusters you want? Yes. Are they round? Yes. You go with k-means. Do you know how many clusters you want? Yes. Are they round? No. You go with DBSCAN. Do you know how many clusters you want? No. Is there noise outliers? Yes. You use DBSCAN. Do you know how many clusters you want? No. Is there noise outliers? No. Use Hierarchical.
Okay, so that's the visualization. And we came with a comprehensive table. And with this, we compared the feature. In feature, we look at the K, the shapes, the outliers, the speed, the parameters, the visualization, and the data set they're best for. So we looked at the three models. So you can read through the table too. Go ahead and read.
Okay. Feature specifically K, cluster shapes, handles outliers,
No.
speed
So you read this way,
parameters.
you read laterally. That means you read horizontally. So the first feature is K. Do you want to
Yes.
specify K? So you read it against the K means, then the hierarchical, then the DBSCAN. Okay.
Features specify K. K means yes, required, hierarchical, optional, DBSCAN, no, finds it.
So what do you understand by that?
That if in about the specifying of K, when you're talking about K means it's important to find K. When you're talking about hierarchical, you can decide or not if to find K, and the DBSCAN you don't have to because it finds it.
Cool. That's lovely. The next one.
Cluster shapes, K means spherical only, hierarchical, mostly spherical, DBSCAN, any shape.
Continue.
Handlers, outliers. K means no. Affects controids. Affects controids. Hierarchical, no. DBSCAN, yes. Marks them. Speed. K means fast. 0 and K. Hierarchical, slow. 0 n to the power of 2 or 0 n to the power of 3. DBSCAN, medium. 0 n to the power of 2. Parameters and clusters. K means and clusters. Hierarchical and clusters, comma, linkage.
You remember we talked about linkage? We gave some examples of linkages. Do you remember? Linkages, complete. You remember? Simple.
Um, complete, simple,
Average,
um,
and word.
okay.
Remember now? So we have which one is the most commonly used?
Complete.
No, it's word. Word is most commonly used. Okay.
Okay.
Okay, that's the linkage. Continue.
DBSCAN EPS means samples, minimum samples.
Okay.
Visualization, scatter plus K means scatter plus interest. Hierarchical dendrogram. DBSCAN scatter plus noise.
Okay.
Best for K means large data sets or known K. Hierarchical, small data sets need hierarchy. DBSCAN or known K, weird shapes.
Okay, so that is the outlook of how each of these models, how they fit in to different use cases we might be faced with. So we don't need to say this is the best one to use, or it's not this, it's not that. It depends on what we are dealing with. So if we're dealing with a weird data set, we need to use DBSCAN. If we're dealing with a large data set and we already know the K, the number of clusters we want to form, so we just use K-means. Then if we want to, we have small data sets, then we need hierarchy, so we use hierarchical. So it depends, our choice will depend on what situation are we dealing with. So we don't need to cram anything, we don't need to, there's no one cap fit it all. So what determines the cap we wear is the occasion. So the cap we wear will be determined by the occasion we're going for. So the same thing in this matter. So I think we've done enough here. I will encourage you to read the notes back. I sent the code to you. I also sent the videos. So just go in there and go through them. Those are things that will really help you. And lay your hands on the code and do some justice to them. So for today, what I'm going to do now is I'll go to the last stage, stage 10, in this clustering topic. I hope you have been able to discover some new things all across this module. Have you been able? Okay. So we'll be rounding it off today. To that end, I'm going to be using the last part, or the stage 10. We're at stage 10 now. And here we'll be looking at feature scaling for clustering. So this feature scaling, again, is something I've expressed before over and over, but I'm still not going to, there's no overflogging the matter because it's so important. So I'm going to take you through what we need to know, or what you need to know in this matter, and then we'll see how well we've gone. So that will be the stage 10. And after that, we'll move to another topic, which will be one of the most important topics in this study, or in this tutorial, in this exploration. That will be neural network. And that powers most of the applications and the advancement we have in the artificial intelligence today. Is that okay? Hope you are listening.
Yes.
Okay. It seems far from what you're doing. Are you close by? Are you close by?
Yes, I'm close by.
Okay, good. Now let me ask you this. What do you mean by feature? What do you understand by feature?
It's a characteristic that something has.
Yes, yes, good. So in the light of what we've been discussing so far over the weeks, what do you really understand it to be? So just give a tangible example to buttress the defense on what, I mean, your understanding of what feature really means. Just give an example. Make it real.
A real life situation?
Yeah, real life examples. You could draw from one of the examples we've used in the course of these courses to explain features. So just give an example of a situation and give the features there. Okay, I'm listening.
So maybe it could be a group of people surrounded in a field and you want to find them, right?
Okay.
So you use some flags, and the people nearest to their flags will go towards it. The
Okay.
features could be the flags, the people, yeah, the flags and the people.
Okay. We are making some progress. Now, use an example. Use this. One of the data sets we used in this class was the housing data set, California housing data sets, where we made classification and we made predictions of the price of a house. Can you tell me some of the factors or some of the characteristics that determine the price of the house at the end of the day?
The characteristics that determine the price of the house are the amount of rooms,
Good. The amount of rooms, okay?
the floors,
The floor.
where it's
What?
located, where it's located.
Where
The
it's located, yeah, the
ubiquity.
location, the
Yeah.
number of rooms, the location, okay?
Mm, maybe I already said the floors, right?
Yeah, the floor. You talked about the floor.
Mm.
Although in that data
Hold
set, the
on.
floor was not there, but I understand what you're saying. But of course, the location was there in the data set. The what's it called? The number of rooms was like actually that's one of the major determinant of the price of the house. Okay, so that means you have the idea of what feature is or what features are. So features are what determine the characteristics of a particular example you're considering. Now, if I look at the student and I'm considering, will this student pass an exam or will he fail an exam? So what will be the features I'll be considering?
The features you'll be considering if the amount of hours he studies,
Good,
the amount of time he sleeps,
good,
the time of the amount of time he plays,
okay,
if he pays attention in class,
okay,
his past exam score.
okay. That's lovely, lovely. So those are the features that I'll be looking at when I want to see, is this guy going to pass the exams or is going to fail? So just this thing you have mentioned are very critical factors I'm going to consider in the light of whether this guy is going to pass the exams or is going to fail the exam. There is no denying that fact. And I love those examples you have given. Now, the next thing now, as I said, will be how do we scale these features? So it turns out that some of these features, you you have some of them in numbers that are far from the other ones. For instance, the number of rooms could be one, right? Could be two,
Yeah.
could be three, maybe five at most. So you have one, two, three, four, five. Those are the number of rooms. But you want to look at the how big the room is. Okay, that's you could use number of rooms. Now let's say we want to also discover the square meter of the rooms. And now we're looking at, let's say we're looking at 2,400 square meters, 3,800 square meters. So in what order are we counting? We're counting the order of what?
The rooms.
No, thousands. I mean, I said 2,000
Okay.
something, 3,000. Then when we're talking about the rooms, what order were we counting? Using
Oh,
100 tens and units. Unit, is it unit? Is it tens? Is it 100? Or is it 1,000? Number of rooms. So we said
Units.
one, two. So we're counting the order of units. One.
Yes.
So all of them are just single digits. One is a single digit. Two is a single digit. Three, four, five. So imagine you're now matching up the numbers, units against thousands. That would be unfair. So there's need for scaling. Is that cool?
Yes.
Okay, so we'll be going there. I'm going there gradually. So let me switch back to my screen and explain this now. Okay, so the objectives we want to cover here, number one would be to understand why different scales cause problems. Then learn standard scalar and min-max scalar. So we've been using standard scalar before in our previous classes. So we also want to learn about min-max scalar. Then we want to see the dramatic difference scaling mix. Then build a complete clustering pipeline. So let's start. So this will be the objectives. We understand why different scales cause problems. We'll learn standard scalar and min-max scalar. Then we'll see the difference, dramatic one actually, just very dramatic, different scaling mix. I will build a complete clustering pipeline. So you are used to this, friends, NumPy, Matplotlib, sklearn. So here now we are importing k-means from sklearn.cluster. So we are just focusing on k-means algorithm. We could have used a hierarchical agglomerative, that's agglomerative. We could also have used DBSCAN, but we just want to use a model, an algorithm k-means to justify this particular concept we want to cover. So in part one, what I want to look at now is the idea that when you use these different scales, you have unfair influence. We have considered this before, and you actually did see the picture then. So imagine that you're comparing houses, what I just explained now. The size of the house is in the order of thousands, between 1,000 to 5,000. So you have large numbers, isn't it?
Yes.
Then you're now considering bedrooms in the order of units 1 to 5. Those are small numbers. So when we calculate distance between them, so this 100 square feet difference, we create a distance of 100. A 2-bedroom difference will create a distance of 2. So the result will be that the size, because size is having 100, so size is going to dominate. So we're going to have a mismatch in our output or in the model prediction. We're going to have some mismatching, and we're going to have some biases. So size will dominate completely, and bedrooms will be ignored because we already have 100 associated with the size as a feature, and we're having 2 associated with bedroom as a feature as well. So that's why we need to scale. Look at this code. So in this code, we just created some clusters, 3. So this is a cluster, this is another one, this is another one. I want to compare scale here. So the size range is between 1,117 to 4,488 square feet. The bedrooms ranges from 1.4 to 5.8. So you see that the size will vary by the around 3.3321. When you subtract these from these, then your bedrooms will vary by, you subtract 1.4 from 5.8, that'll be 4.4. So now let's see something. So we have seen what we have. We want to do without scaling. We don't want to scale. I want to see what we're going to have. So we want to use k-means to do a clustering exercise here, but we're not going to scale. And what do we mean by we're not going to scale? So we're going to use k-means as a class, and we are going to instantiate an object km underscore unscaled using k-means. And you remember, we need some parameters. We said the most important parameters is the number of clusters, n clusters. So we have associated 3 to it. Random state is another parameter. Then n init is another parameter. You remember we said we normally use default of 10. Now yes, we have labels on scale. So here we want to fit and predict. Fitting means we train. We want to train the model and now make prediction. That's what we're doing. So we're doing those two. We are fitting and we're making prediction. And we're taking houses as the argument. And our houses has been defined here. So in our houses, we have created a list using VStack. So I've explained this also before now. Now, let's see what we have here. So we're going to do a scatter plotting. And for this scatter plotting, we have two sets. So we're going to do plot scatter using houses. So this means take all the rows and the first feature, the first column. Then that is for the x-axis. Then for your y-axis, this column means take all the rows, then comma, take the first column. So that's what this means. So it will plot x as all the rows. That means all the features will be considered and the first column. Whatever the first column is, I think that should be the size or the number of bedroom. Then let's see, then you take, what's the first column? So we have, okay, size, the number of bedrooms. Okay, size and bedrooms. Okay, the next thing is to, okay, this is just normal plotting. I'm not going to bother about it. So let's run this code. So in this code, we have, we've generated 3 clusters. Okay, so just take note of what we have here. So from this, we notice that the algorithm only sees horizontal differences. That's the size. See, it only sees the difference between the sizes. So that's why it the graph scales out, it extends. Bedrooms are almost completely ignored because their values are 1,000 times smaller than size values. So you can see here, this vertical axis is where we have the size from 0 to 6. That's the number of bedrooms. And here we have 1,000 to 4,500 for sizes. So sizes actually dominate in this matter. And the reason is not far-fetched. The ratio of bedrooms to, or of size to bedroom is in the order of 1,000. So that's why we have this type of output. Then take note that this is unscaled. We didn't scale this. So we're going to get to a stage where we're going to scale and we're going to compare the results. You will see the difference. So the next step is that we want to use or introduce feature scaling. So in feature scaling, we're going to consider 2 major ones. I said before that we're going to consider standard scalar and we're going to consider min-max scalar. So there's a statistical expression or formula behind it. So let me just talk about it in a jiffy, just know what they are. Standard scalar, min-max scalar, but the math behind it is stated here. So when you take standard scalar, so standard scalar is also known as Z-score normalization. Z-score normalization. Can you say it?
Z-score normalization.
And this is the formula. You see this X, it takes the X, that's your value, the data point, your value X. This mu is a means. So it will subtract your means from your X, then to divide by the standard deviation. So that's how to normalize. So here, centers data at 0, scales to unit variance. Okay. Then the next one, sorry. So the next one would be the min-max scalar. So for the min-max scalar, we just subtract the X minimum from X. Thereafter, we subtract X minimum from X maximum. That's how we scale that. And so what will happen is that it will scale to a range of 0 to 1. And this is very good when you are dealing, when you want to band the values between 0 and 1. So whatever you have here, it cannot be lesser than 0 and it cannot be greater than 1 because you have subtracted the same factor from both sides, from both numerators and denominator. So you have subtracted X min from your X, then you subtracted X min So you have subtracted equal value from both numerator and denominator. So you're going to have a scale of 0 to 1, a range scale of 0 to 1. Okay.
Yes.
So this is just a formula for that. Okay. The next thing is let's apply. So whenever we are calling standard scalar or we're calling min-max scalar, what our model is actually using is this. It's actually using this. So there's nothing. So under the hood, this is what is expressing. And at the end of the day, we'll now have uniformity in our scales. Okay, let's apply standard scalar here. Let me explain the code again. They are not strange. Just take note. So we are calling standard scalar. I've explained this in the previous classes, so I'm going to go it again. Standard scalar is a class. So we are calling it. So you remember we're instantiating an object scalar using standard scalar. So that means this scalar will inherit everything the standard scalar class has. So now we have scaled, we have called the scalar. I've called the standard scalar on scalar. Okay, on object scalar. Then we'll go ahead. After calling it, you now do what you call fit transform. You fit transform. So houses scaled, we need to fit transform houses. Now here we can transform all the data for houses because what we're actually dealing with here is on clustering, is a clustering algorithm. If this were to be if it were to be supervised learning, it will only be our training values, training data that we're going to fit transform. We're not going to fit train our test variable or test values or test features rather. So it's because we don't have any test, we don't have any true value or true table, true grant in this matter of clustering. So that's why we fit transform everything, all the data that makes up, all the data that make up the houses. So houses scaled. So we call scalar dot fit transform and we pass in houses as an argument. So this will ensure that all the data points inside that makes up the houses, the features that make up the houses, all those values have been scaled, transformed, and fitted. Okay. Now let's see this plot. What I want to do with this plot is I want to compare before and after. So I want to create subplots. So the subplot will be 1 row, 2 columns, 1 row, 2 columns. That's 1 by 2. And that means we'll be having this before on one side, the after on the other side. So before scaling, we create an axis of 0. So that's index 0. Then after scaling, we have axis of 1. Okay. And to create before scaling, we use scatter plot. And this scatter plot will refer back to our houses data sets. We explore all the rows. That's what this colon is doing. All the rows, command. Then the first column, that is the first index 0. That will be the x-axis. Then the y-axis will still be the houses data set. You take all the rows, then the 1 means the second features. The other ones are just settings. This gray color, the settings, the size of your shape. Okay. Then this one is also set label, X label, Y label, set title. Then the grid, we want you to have a rectangular-like shape at the background. Then alpha, I want you to be transparent. So all these are just settings. The main thing, the main plot is handled by the scatter, houses, index 0 of the column 1, then houses, index 2, that's the, sorry, index 1, that's column, second column. Okay, and this will undo the after scaling. The same principle apply, So we're just replicating this. So we're only changing. Now we're using houses scaled. Houses scaled. This houses scaled. So we have scaled the houses and it has been saved in this new container called houses scaled. So we want to compare them. Now let's run this code, which you can try by yourself and see what we produce. Now look at this first one. So you see how expansive this first is before scaling. Look at this second one. What can you say about this? Can you compare them? Compare the two shapes.
Okay. So before scaling, it looks a bit wider and the clusters are a bit separated. After scaling, it seems to have gotten less wide, like standard or normal.
Okay. Then as it relates to the numbers, the values for both X and Y axis, what can you say about them? Compare the before and
It's
after.
reduced because it goes from 1, 2, 3, 4, 5, 6, and 1,000, 1,500 to 1.5, 1.5, 1, 1, 0.5, 0.5, 0. It's more balanced.
When is it balanced? When is it more balanced?
After scaling.
After scaling. So you see there's a lot of disparity in the scalings at the first instance, that is before scaling. Now after scaling, you see we have the same mismo, they are not mismo. So we have minus 1.5 to 1.5 at the x-axis, then minus 1.5 to 2.0 at the y-axis. So you could see now that they are balanced, and you can see the shape that is generated. So there is a compact shape compared to the first shape where the sizes just dominated the model. Does that make sense?
Yes.
So after scaling, the size mean becomes 0. So this is a key thing you must take note of. After scaling, when you call standard scaler, what standard scaler ensures is that standard scaler will ensure that your mean is 0, then your standard deviation is 1. Now what we now have is that the bedrooms, the mean is zero, then the standard deviation is 1. So both features now have mean of 0 and standard deviation of 1. So they are now at par. They are at the same level. Okay. So let's look at cluster with scaling. So cluster with scaling, which we have actually demonstrated. So let me just run this. And beyond just plotting and visualizing, there is another intricate point we want to bring in. And that has to do with the performance, the results. Now look at this. We want to calculate accuracy of our models with scaling and without scaling. So that's why we're importing adjusted rand score from metrics. And the adjusted rand score takes true labels and label unscaled. So we want to just check the accuracy. We want to see, apart from the visualization we have seen, is there anything else that really shows that there is need for scaling? Is it only just that S sizes is dominating or something else? So let's see something else. So the code still remains the same largely. So you see, it's still k-means we're using. So, okay, before I forget, I want you to repeat this procedure with the other models, the DBSCAN and the Hierarchical. Please repeat them, scaling and unscaled. Just replicate what we have here. Please, I'd like it to be submitted in 2 days' time, okay? Does that make sense?
Okay.
Okay, please, I'll be expecting that. So you'll just replicate, just look at, study the k-means and replicate same for DBSCAN and Hierarchical. So again, we are focusing on k-means here. We pass in these 3 parameters. We have the number of clusters, random state, and the init function, the init number here. The same thing happened. So the plotting without scaling. So we use our original coordinate for visualization. So we use 0, that's the first column. So we take all the features, all the rows. Then we take the first column, all the rows, we take the second column. And this one is just to pass some settings. So we set the X label, set the Y label, set the title, then the grid, we put in some rectangular shape like this. So with grid, what grid does, sorry, is square shape rather. So it creates this square shape object. So if you don't put grid, if you switch off the grid, nothing will be here. So those lines, square formation lines will not be part of the graph. Okay, so that's it with this one. And the same thing is applicable to the scaling aspect. Only that instead of using houses data, we are using scaled. We've already scaled it. So that's what we'll be plotting on. Oh, sorry, with scaling, showing original. So we are accessing the houses, okay. And we have this. So we have this. Okay, so we want to maintain. So at this point now, we're maintaining the houses data set. It is at this point we want to create the accuracy. So let's see what happens here. So for this graph, again, you see with scaling, this is with scaling, and this is without scaling. So what has happened here is that in terms of clustering quality, so I'm checking the adjusted rand index, so which has to do with the clustering quality. So you will notice something. Now, first of all, there's a point here. Look at this. Look at this. Let me point at this one. If you look at this, you will notice that it's not appearing here. It's missing it. So that means the scaling, the clustering quality is lower here without scaling than in scaling. Okay.
Yes.
That's just one thing. So without scaling, the clustering quality is 0.966. That's 96.6%, approx 97%. With scaling, you have 100%. So that's 3% difference is something. Scaling dramatically improved the clustering. So it could be more than this if we have to deal with some data set maybe that are larger than this or that are much more nuanced. So the improvements could be much more higher than this. So the bottom line is that whenever you're using scaling, it improves your output. Your adjusted rand index, your array will be improved. So it's good to scale. Now, at this next stage, so we have seen why we should scale. We have seen that it is non-negotiable as it is. So we need to scale. So the next thing we want to do now is we want to explore a pipeline. When we say a pipeline is like an entire structure, end to end, from beginning to the end. So we want to have a complete clustering pipeline. In this complete clustering pipeline, we want to calculate the slowed score, then use pipeline. So this pipeline, what it does is that it joins your models together. Every module in your model are properly joined. So it's very important, especially when you want to use it in production. When you want to use it in a project, it's good to use pipeline. So we're importing pipeline here, and I'll be using it in this regard today. So again, we'll be using silhouette score.
Okay.
That is metrics. So be importing from sklearn.metrics, we'll be importing silhouette score. In the sklearn pipeline, we'll be importing pipeline. So here we needed to create a function to achieve that. So what we are defining here is just, well, let me quickly explain the code. So we are creating a function called that we have tagged cluster with pipeline. And this takes in 3 arguments. It takes in X, it takes in N clusters, it takes in scalar type, and in this case, it's taking standard one. So what are we using this function for? So the docstring document, these are docstring. It shows us what this function is performing. It's a complete clustering pipeline. Sorry, pipeline with scaling. The parameters, the X is the data array. The N clusters is the number of clusters. The scalar type is standard or min-max. So the default here is standard. You could make it min-max depending on what you want. But if you don't set any standard, I told you that we are using two types here. We are using standard scalar, which we have been using before now, and the min-max from the statistical calculations here. I also show that. So this is the standard scalar, and this is the min-max scalar. So if you don't specify any, so it will assume you are using standard scalar and it will take standard. Otherwise, it will take your min-max scalar that you set. So that's what we're trying to achieve here. Okay, so we said the scalar type will be standard scalar type. So here we creating the body. You remember when I did treat function creation in Python, I said whenever we are creating functions, we have the keyword def. This is a reserved keyword. Then we have the name of the function, followed by the parentheses, and inside the parentheses, you will pass in the argument you want to have. So here we have set 3 arguments. Then you're going to have the docstring that will explain to others what your function is performing, what function is performing. Then you're going to give us the body of your function. So in this case, the body is, so choose scalar. So to choose scalar, so it's telling you, it's using a conditional statement. If, and you remember we have treated this before, if scalar underscore type is equal to standard. Now you can see that this double equal to, it means equal to in the recess of mathematics. 1 plus 1 is equal to 2. But when you use it once, it means assigned. Assigned is when it's 1. Then when you use double, it means equal to in the recess of mathematics. So here it says, if scalar type is equal to standard, that means if you are using standard scalar type, scalar will be scalar object will be instantiated on scalar or standard scalar. Otherwise, that is else. Scalar is min-max scalar. I just explained that before. I did explain it. That's the part for 1, how to choose a scalar. Then scale the data. So the next thing is in this body of function, and that will be to scale that data. So our data will be scaled by calling the scalar object and joining it with the dot operator, and we use fit transform to change, to transform the x that is passed in. So we're passing x in. Whatever we have set our x to be, we're going to pass it in, or whatever we've defined it to be, we pass it in. And this function, this part of the function, we create a scalar on it and transform it such that the main will be what? 0. So standard scalar makes your main to be what? Hello, are you there?
Yes.
Standard scalar makes your main to be what?
To be more based.
To be 0. To be 0.
Yes.
Standard scalar makes your main to be what?
To be 0.
0. And it makes your standard deviation to be 1. Say standard deviation. Say it.
Standard deviation.
So it makes your standard deviation 1. It makes your mean 0. Can you say it with me? Standard scalar.
My standard.
Makes your
standard
mean.
Scalar.
Makes your mean
makes
0.
Your mean
0.
0.
And standard deviation 1.
And standard deviation 1.
Okay. So that's what will happen here. So when x is scaled, then the next thing is to do the clustering. So here, your cluster, you again create an object, KM, instantiated on KMeans class with this argument. N clusters is N underscore cluster. That means it will take this number of clusters, whatever you set for it. Random state will be 42. Then N init will be 10. Then the next thing will be to fit predict with a label called labels, whatever. You can make this anything else. So you've chosen scalar, you've scaled the data, you've clustered. Then we now want to evaluate, want to see the results. So here we are using silhouette score. And we are passing in the x scaled the scaling we have performed, and the labels. That means the fit transform. So the function, we ask our function to return labels, to return for us the score, and to return for us X scaled. So after we have set the function, so the function has been defined. Now the next thing is we want to use it. And to use it, we pass in 3 labels or 3 containers or 3 variables. We call labels, score, and X underscore scaled. Now we pass in the pipeline. Cluster with pipeline is what we are using to generate these 3 variables. And it will take houses and number of clusters as whatever. And we're taking 3 here. So we're using cluster with pipeline. So here now we're using the function. This function we have created, we're using it. And we're using it to create. So we are passing in the houses as the X, the N clusters as 3. Then the scalar type would have been undone at this stage. Okay, so far so good. I believe I have done justice to the code.
Yeah.
Okay, so let's run it and see what we have. So we have used this. Where is my? We've used this function cluster with pipeline, and it has returned for us a silhouette score of 75.9%. That's like 76%. You did remember when we're treating silhouette score, we said any silhouette score above 70 is a strong silhouette score. So this is a strong one. So we use this pipeline pattern for clustering. So anytime we are using clustering, always make sure you use pipeline. So pipeline, we join everything together and to be a compact container. Everything is inside of it. Imagine you buying a box of, you're buying a TV in the market, in the supermercado, and they will give you a bunch, just a box. And inside that box, everything you need will be in there, isn't it?
Yes.
The TV itself, the manual will be there. The tool you might use to screw some bolts will be there. Some screw and nuts, bolts and nuts you need to be. Everything you need will be fitted in, will be there. Or you are buying a new phone. So they'll give you, they're just going to give you a pack. And inside that pack, everything about that phone is fitted. So that's what pipeline does. So pipelines bring everything together. So it will not look like, oh, you want to use your phone. Now you are looking for battery somewhere, so you need to go and buy a new battery. It doesn't work that way. Pipeline brings everything together. Okay, and that makes sense so far. This one, I want you to do some, this will guide you in the assignment I also gave you. So you want to make a template of this. So I told you earlier on to try these models on DBSCAN and also on Hierarchical. So what I'm adding to it now is that I have used K-means to create this pipeline. That's it.
Yeah.
Now you're going to copy this and you're going to modify this to, so for instance, where you have K-means here, you are going to import DBSCAN. For DBSCAN,
Okay.
you're going to import then the agglomerative also for the hierarchical. So you do it, you repeat it for each one. And there are other things we can also do.
So I switched the K-means to agglomerative and DBSCAN.
Yeah, but you do them differently. The DBSCAN for DBSCAN, the agglomerative for agglomerative.
All right.
Okay. Okay, so you can practice this. Practice exercise. Okay, so this is just to practice, and you can use this as a code. So let's do summary. So the first rule is always scale your feature before clustering. The number 2, use StandardScaler as it usually is the best choice in scaling. Then apply scaling, same scaling to train and test data. Then evaluate before and after scaling to verify your improvements. Then finally, the pipeline must be used. Try and use pipeline. So where you have the scalar, you have the k-means, and every other thing you need to fit in. So the pipeline is the scalar fit transform, and the fit predicts of the model. So I've completed the 10 modules, the 10 stages on clustering, and it has been a glorious and wonderful journey. I think this is enough for today. I was thinking we'll be able to go to another topic, but that will be overloading you. So we're not going to go into that today. So go and try out those stuff I've given you as homework. In case you miss it, listen back to where I put it in the video and get the assignment clear. They'll be very easy for you to do because you already have a template that you're going to follow. So do you have any question?
No.
Okay. On that note, then we can call it a shout out today.
All right.
Thank you. God bless you.
Thank you.
You're welcome.